Hello, greetings, people of Earth. I come in peace. Hello. Welcome to the Ask Abhijit show. Today we are talking about science. A very nice, non controversial topic. No geopolitics, no history, just science. So let's see who all is here with us. I can see Zaina, Samarth, Tejas, Siddharth, Srushti, Shivansh, Nishit, Bikram, Ganga Singh, Crazy Brain, Alpha, Nandish, Chiching, Cupcake, Priyanshi, Parag, SR, SJRIKK, Dongar Singh Chauhan, Vijay Vakela, Vihan Shergil, Kumwar, Shubham, Vladimir Adityanath, Ganga Singh, Bikram Ghosh, Animish, Shweta Arushi, Alpha, Kiran, Darshan, Sagar, Rocky, Nirav, and a whole lot of people. Great to see you all. Great to see you all. So let us go into the questions. I have, as always, picked up a bunch of questions that you've asked, and I will endeavor to answer as many of them as possible. So let us begin with the questions, and let's begin with this one. So Swapnil says, is terraforming the Sahara Desert or Australia possible for making a place habitable, or would it disrupt weather and climatic patterns around the world? Terraforming the Sahara Desert or Australia. See, the Earth is a single system. The atmosphere, the land, the oceans, it's all tied together in a, well, everything is interrelated. So if you change one aspect of any of these things, everything else will kind of react to that. So if you say you want to make the Sahara Desert lush green again, it's possible. It can be done with engineering projects and all. You dig, you create canals that bring in water from somewhere else, possibly, uh, or some other means of doing it. So yeah, you could possibly do it over a period of time, maybe 50 years or so, because these projects would take time. So it would certainly make the place more habitable. You could do it in the Australian outback. Australia is a very dry, arid place, most of it, the entire continent. It's possible to do that. It would certainly change the weather and climate patterns around the world because it's all interrelated. Uh, so certainly it's possible, but it would definitely change things around. Now, in the past, we know that the Sahara Desert was lush green, maybe 100,000 or so years ago, or maybe before that. There have been these cyclical patterns in the history of the Earth in which there are times when there are this cold weather, the ice age, and all that. There are times of dry climate in the Sahara, like we see now, and there are times when there is much more rainfall and places are more lush green. So it's been there. But if you change this, you will certainly see the entire world's weather change and the patterns change. The monsoon may change in India depending on various factors. So it would certainly change. It would not disrupt weather and climate, it would change weather and climate if you make such large scale changes in the geography of the Earth, right? Okay, the next question is about climate change. Climate change is a very important thing. So, for 30 to 40 years down the line, what are the major changes that are going to happen to the Earth's climate? What will be the consequences? And something geopolitical game going on. See, climate change is a thing. There's no doubt about it. It's always been around. Climate change is something that you cannot really question. It's there. So what's going to happen in the next 30, 40 years? We know that the amount of uh, carbon particulate matter in the atmosphere is increasing. It's at maybe an all-time high or something. I don't have the statistics. You can look it up. Um, so what that does is that it intensifies the global warming. It causes this greenhouse effect, and it's making our climate warmer. I believe in the next 100 or so years, we are projected to have a rise, an increase in the average global temperature by maybe 2% or so, which is significant. 2% may look a little very small, but in the global context, it's quite high. It will cause uh, a lot of ice to melt in the polar regions, mostly Antarctica, the Arctic region, in the north, near the North Pole, and you're already witnessing this. You're seeing this happen. Now, climate change has always been a thing. It's always been around for millions of years, hundreds of millions of years. If you look at the entire geological history of the planet, it's been a constant story of climate change. Even in India, 7 8,000 years ago, the Indian monsoon was much more intense. There used to be much more rainfall about 8,000 years ago. And then about 8 or so thousand years ago, 6,000 BC onwards, the monsoon started declining monotonically. And today we receive far less rainfall than we used to receive 8,000 years ago. And that caused a lot of changes in India. An entire river disappeared, right? And so on. So these things have always been part of our history, but right now there is a significant man-made component to the climate change. And because of that, we are witnessing global warming. So in 30, 40, 50 years, we're going to have an increase in the global temperatures, average temperature. So let's say you are in a place where the average temperature today is 25 degrees throughout the year. If you average the temperatures throughout the year, you get an average of 25 degrees. Maybe in 40, 50 years, it may be 26 degrees, right? That sort of thing. So you're going to have these changes. The ocean levels will rise as the ice melts in the polar regions. And in 50 or years or 100 years, many of the low-lying areas, the coastal regions in various parts of the world, could kind of go underwater. You may have an increase in the average water levels, sea levels worldwide, maybe by, I don't know how much it's exactly going to be, a foot, 2 feet. That's a lot, actually. So many low-lying island nations could disappear. There are some island nations in the South Pacific region, small island nations that could be in trouble. The Maldives could disappear. Bangladesh could have a lot of trouble, and people are saying that India should absorb uh, the Bangladeshi population that will be affected by this. So all of these things are going to happen. We're gonna see this even in India, in various coastal cities, Kolkata, Mumbai, Chennai, etc. You could see some consequences of this rise in the sea level. So if you're planning to buy property somewhere in one of these metropolitan cities, you may want to buy it on higher ground, uh, at some distance from the sea coast, perhaps. So that's the kind of thing we're gonna witness. It's gonna happen. It's happening. It's a process that's already in motion. With the geopolitical game going on, is it stoppable? You can't stop it. It's what we can do is we can try and prevent further change. We can try and slow down the pace of change. We can try and ensure that we don't dump more pollution, more carbon into the atmosphere. We can try and reduce the carbon output, the carbon footprint of every country, and so on. That's what we can do. But what's already going on cannot be stopped. It's going to happen. It's going to happen anyway. uh, so it's almost impossible to stop this, because every nation is competing with each other. There are countries that have been destroyed over the past 500 years by colonialism. They want to rise again, and the only way to rise again is through industrialization. Industrialization has a carbon footprint. What can you do about it? You can't ask the countries, the West cannot ask the countries it has destroyed in the past 500 years to stop developing. It just won't work. So it's just a natural consequence of development, and development is required. We have such a huge population. So there's a whole range of factors in this, but it's going to happen. It's happening. Okay, Tejas asks, is it possible that Jupiter has eaten up other planets, as some latest study suggests? Right. So what is Jupiter? I hope you all know the solar system, what it's like. Can you name the planets? Can you name the planets starting from the sun onwards? So let me tell you, we have the sun, then we have Mercury, Venus, then the Earth, then you have Mars, then you have the asteroid belt, then you have Jupiter, Saturn, Uranus, Neptune, Pluto. Then you have further, uh, there's a whole bunch of planets called the not planets. Even Pluto is no longer classified as a planet, and so on. Then you have the objects that are beyond Pluto, the minor planets, the planetesimals, you have the Oort cloud, comets, much more. The Trojan asteroids, various other asteroids, and so on. So we're talking about Jupiter. So Jupiter is the largest planet in the solar system. It's also believed to be it is also most likely the oldest planet in the solar system. It's the first overall planet that formed out of the protostellar gas cloud, right, from the primordial solar system. Um, so the solar system's age is about 4.57 billion years. Yeah, and Jupiter is believed to have formed the solid core of Jupiter is believed to have formed about between 1 million years and 5 million years after the start of the solar system's history. So it's the oldest planet that we know of. Earth. So Jupiter is about 4.5 billion years old. The Earth is also about that old, but slightly younger than that. And as we know, Jupiter is about 320 times the mass of the Earth. It is 1,000th the mass of the Sun. So that's about Jupiter. So is it possible that Jupiter has eaten up other planets? It is entirely possible. See, the early solar system was a very dynamic place. There was a lot of chaos. It's possible there were certain planets called super Earths that were formed possibly in the inner solar system. Inner solar system means the orbit of uh, between the sun and the present day orbit of Jupiter. It's present that certain very large rocky planets were formed in the early solar system uh, in this period, right? And because of the very dynamic nature of the solar system at that time, there would have been collisions between these super Earth like planets, which possibly gave rise to the asteroid belt that we witnessed between the orbit of Mars and Jupiter. It's also possible that Jupiter was earlier formed. When it was formed, it was at a different location, at a different distance away from from the sun, maybe much further outwards. And then because of the gravitational dynamics, it came inwards and it shepherded certain planets, and it gave rise to the order that we see today. So it is certainly almost 99.9% probable it has eaten up, swallowed up ancient planets in the past. And certainly lots of debris, rocky debris, etc. It has definitely done that. We have witnessed about 20 or so years ago, maybe before that, the crash of the comet Shoemaker-Levy into Jupiter. The gravity of the planet first shredded the comet into multiple pieces, and then those pieces eventually ended up hitting the planet Jupiter. And this was witnessed. You can see photographs of that available online. And so it swallowed up that comet. In the past, there would have been lots of events like that. Even entire planets would have possibly been swallowed up by Jupiter. So I don't know which study you're referring to, but it is definitely very likely that this happened. Even Saturn would have swallowed up certain planets. It's also quite likely that Earth itself, in its early phase, was hit by. We know that there was a massive bombardment, the so-called Hadean period. But it's quite likely that the Earth itself was hit by a large planet in the very ancient past, maybe about 4.4 years before today. And that collision most likely possibly gave rise to the moon, right? So yeah, it's a very interesting history. We don't know a lot about it, but depending on what we see today, we can kind of reconstruct the earlier, older history of the solar system. So yes, it is quite possible that Jupiter has eaten up, like you say, other planets in the past. Okay, Bakhanani says, will humanity ever get success in finding alien life at all? Do aliens exist? If they do, can we ever reach them or get a glimpse of them? Are we really alone in the universe? Excuse me. See, it's possible that we may discover alien life next week. It's possible. It's also possible that we may never ever find aliens, any trace of alien life. Both possibilities are, I would say, equally likely. Do I believe aliens exist? I am pretty sure that aliens exist. I'm pretty sure that life exists in other places, possibly in our own solar system. There could be life in the microbial form or something, maybe on Mars, perhaps buried under the soil, maybe on Europa, maybe on Titan, maybe somewhere else. It's quite possible. Um, so microbial life could exist right now in our solar system, beyond the Earth. When we talk about intelligent life, if you just see the sheer number of stars, galaxies, planets that you have, it's almost impossible to imagine that with 10 raised to 23 or 24 stars in the visible universe. I mean, is it? I mean, if we are the only place where life exists, that doesn't make any sense. So I am personally quite sure that life exists in other places, maybe even intelligent life. Most likely, there would be other civilizations that could be just as intelligent or more intelligent, more advanced, more evolved than us. But for some reason, we are not able to detect them. We have never been able to detect them in recorded history, from whatever we know. There is no unambiguous evidence that we have found aliens in the past. Some people say that there are certain carvings on pyramids or rocks or whatever that seem to depict alien visitations. Well, it's not unambiguous evidence. It seems to look like something that resembles a spacecraft or somebody, or a figure of a human being or something that seems to wear a kind of helmet that you would imagine in science fiction movies, but that is not unambiguous evidence. So so the question is, why are we not able to detect alien life if it should be so uh, widespread and common in the universe? Well, maybe we are not evolved enough. Maybe we are too primitive. We may think that we all think that we are so advanced and all in the modern world. We have all this technology and all that, but most likely we are still a very primitive species, right? Think about it this way. Let's say you have a petri dish in which you have a colony of bacteria. Okay, it's in a lab. It's sitting in a lab. Scientists are studying this colony of bacteria, a few million bacteria in a petri dish, a dish which is sealed. And the colony of bacteria is, let's say, 300 generations old. So bacteria, they divide, they reproduce, they die off, and their descendants again do the same thing. It goes on and on. And let's say this colony of bacteria is, let's say, 1,000 generations old. Yeah. So these bacteria, they're sitting in there and they're talking to each other. They are wondering, do other life forms exist? Yeah. They're having this discussion among each other, these bacteria, that we have been living here for 1,000 generations at least. Our history is very ancient, and we have never found evidence of alien life. They're talking to each other. And just outside what they can perceive, there are scientists, human scientists, who are studying them through the microscope. So the bacteria don't have the sensory apparatus that is needed to see the scientists. The bacteria are so small. The scientists are so far away, relatively, compared to them. So even though the scientists are observing the bacteria have no idea that they are being observed. So maybe we are also, in a way, those bacteria. And maybe there's somebody observing us when we are simply not aware of it. We know that 95% of the universe is unknown to us. It's dark matter, dark energy. We don't have the least idea of what these things are. So maybe there's something going on out there that we're not aware of, and they know we are here, and they may be studying us for a few thousand generations, and we just simply not aware of it. Yeah, the time scales that we live in, 100 years, 70 years, it must be just a fraction of a second to maybe to this hypothetical alien species. So that is entirely possible. So maybe it's all out there, but we're simply not able to see it because we are too primitive and our senses are too limited. Entirely possible. So I don't have definitive answers. Are we alone in the universe? I don't know. I don't think so. I don't think so. Can we ever reach them, get a glimpse of them? Who knows? So let's see how it goes. Hopefully, we will find something. And hopefully, that will not be too dangerous. Yeah. Right. Okay, Dark Lord. The Dark Lord is here. All right. Is time travel really possible? Can you explain the grandfather paradox? And Jasprit Bhai says, according to theoretical physicists, are the possible ways to travel back in time other than wormhole concept, in which there's a requirement of cosmic strings and negative mass and negative energy, theoretically, of course? Can you please share some of the hypotheses about traveling back in time? Is there any solution to paradoxes such as the grandfather paradox, the bootstrap paradox, etc.? Okay. What is the grandfather paradox? Imagine a scenario, a hypothetical scenario in which you can go back in time. Let's say you go back in time 80 years. And then you discover a person, you meet various people back in time, 80 years back in time, and you meet a person, you get into some kind of argument with the person, you end up killing the person. Yeah. And just by chance, by terrible chance, that person happens to be your grandfather. Yeah. So you go back in time, you, for whatever reason, end up killing your own grandfather. Then how is it that you exist? That causes that breaks causality. There is a causal chain in the world. I always keep talking about the causal chain, the cause effect relationship. Everything that exists today exists because of things that happened in the past. The causal chain, cause and effect, goes back millions, billions, billions of years. It goes back 13.7 billion years. The cause and effect chain, which is the timeline of the Big Bang, right? So if you go back in time, if time travel were possible, if it were possible to go back in time, you go back in time, you kill your own grandfather, then how the hell do you exist? It makes no sense, and yet there it is. So that kind of tells you that there is that the causal structure of the universe breaks down if time travel happens, right? Then there is something called, like Jaspreet says, the bootstrap paradox. That's another paradox. Let's say I'm sitting here. Now, I have been studying physics my entire life. I know relativity, the special theory of relativity, the general theory of relativity. Now, who came up with relativity? It was Albert Einstein. He published the special theory in 1905 and the general theory of relativity in 1915. I know these theories because I've studied them, right? I know the equations. I have actually done the work, not just reading popular science books and magazines. So let's say I travel back in time. Yeah, I travel back in time. Go back to 1904, 1 year before Einstein published these theories, the first theory. So I go back in time a year before, or let's say 5 years before Einstein published relativity. I meet Einstein and I teach him relativity. I teach him the entire math, all the equations, everything. I give him the entire theory that he eventually ends up publishing. And then he goes ahead and publishes it because he learned it from me. But I learned it from him. But he learned it from me. So who came up with the theory first? I go back in time and teach it to him, but I learned it from him himself. So who's the originator of the theory? Once again, the causal structure of the universe gets messed up. So that is the bootstrap paradox. There are multiple versions of this. You can imagine all kinds of scenarios in which this thing gets messed up. The bootstrap paradox and all that. Right. So that's what it is. So the question then is time travel really possible? That's a real question. So general relativity permits some exact solutions that allow for time travel, and some of these exact solutions, they describe what is known as they describe universes that contain what's known as closed time-like curves. These are world lines that lead back to the same point in space-time, not only in time in space, but in time as well. So these are called closed time-like curves. So a closed time-like curve, it's a world line of a material particle in space-time. So this world line is closed. It returns to its starting point. So if a particle or a person, let's say, is inside that, you go back. It's like a loop. You can travel back in time. So in this, you can travel backwards in time, but not forwards. So that's called a causal loop. And even when it comes to wormholes, what's a wormhole? A wormhole is like, well, it looks like a black hole from the outside, but it's a tunnel with two mouths and a throat that connects the two mouths. So let's say you have a wormhole which is open for whatever reason. First of all, wormhole solutions are very wormholes want to snapshot. It's almost impossible to keep it open unless you have something called exotic material, like something with a negative mass. We have never seen any material that has negative mass, right? But let's say such a thing, it's hypothetically, theoretically possible. So if you have something like that, you can keep the wormhole open. Or if you have something called a cosmic string, which is a defect in the structure of space-time, hypothetical again. If you have these things, you could keep a wormhole open, and that could then become a traversable wormhole. So let's say you have a wormhole with one mouth in one place, the other mouth far away in space-time, and the other mouth is traveling at relativistic velocities. So if you go from one opening and you end up at the other, you may end up going backwards in time. So these are possible scenarios in which you could actually travel backwards in time. So that's what I can offer you. So these are uh, possible ways in which hypothetically, theoretically, you could possibly go back in time. But the question is, does it violate causality? It could possibly violate causality that we just spoke of, the grandfather paradox, the bootstrap paradox, and so on, if it were possible. Secondly, it could even violate the second law of thermodynamics, entropy. What does the second law of thermodynamics say? Well, one of the ways of putting it is that systems always flow from a state of order to a state of disorder. Entropy always increases. So an object that's trapped within a time loop, or any information that is trapped within a time loop, would continue to age and eventually disintegrate. But does it work that way? So these are the questions, the problems that exist, and we still don't have the actual answers. So that is where we are. So there is something about time travel. It's not entirely verboten. There are theoretical solutions that would allow for possibly for time travel, but there are many unanswered questions about causality, about the second law of thermodynamics, and all that, right? So that's a little bit about it. Very interesting subject, very fascinating subject, and a lot of theoretical research is going on about this as we speak, about the causal structure of the universe. Does it violate causality? Uh, could there be an event horizon within within a wormhole, possibly, that would kind of preclude, that would kind of make it possible to travel without violating causality? All kinds of such research is being done, and it's a work in progress. Okay, the question is, this is a question about, okay, what is the world's first liquid mirror telescope developed in India, and how would it be useful for scientific discoveries? Right. So I think it's been installed at the Devasthal Observatory. Let's take a look at that. I typically don't bring out the map in science episodes, but let's do it. For a change, let's bring up the map. Let me open the map first, and we will go and try and find this observatory. Where's the map? Here's the map. Come on, map. Okay, so let's Devasthal Observatory. It's in northern India. It's in the Himalayas. Let's see what it brings us. Okay, let's bring in. Okay, so this is the Devasthal Observatory. Where is it exactly located within India? As you can see, it's in northern India. Yeah, that would give you the context. It's west of the Nepal-India border and south of the India-Tibet border. So that's where it is. It's high in the Himalayas. It's in a mountainous forested region. And we have the ILMT, the International Liquid Mirror Telescope, over here. So that's where it is. That answers where it is. Now, what is this thing? Right? So it's not the world's first liquid mirror telescope. There have been liquid mirror telescopes in the past. It's the largest that exists as of today. And it's not been developed in India. It's been developed by a consortium of, I think, 3 nations: India, Belgium, Canada, as far as I can recall. So you can look up the details. Now, what is this? So in a telescope, you typically have a lens or a mirror. In large telescopes, you have reflective mirrors, and these are parabolic mirrors typically. Yeah, and so what you do is you take a big piece of glass, you shape it in the proper shape, the parabolic shape. Then you have to apply a coating of some kind of reflective material, typically some sort of metal. It's a long, involved process. It costs a lot of money, right? So there, in this Devasthal Observatory itself, there is another telescope which cost about $20 million to make. And this new telescope, the liquid mirror telescope, costs about 1/10 of that to make. So in a liquid mirror telescope, what you have is that you have a liquid metal, typically mercury, that is set spinning. And when you do that, it takes on the shape that's the parabolic shape that you want in a telescope. So and it's put in a cushion of air or something, some sort of technological thing is there. And the mirror, the liquid metal, the mercury it assumes that parabolic shape, and then it can be used as a very good mirror for a telescope. The thing about a liquid mirror telescope is that you can't maneuver it. You can't make it point to a certain place in space, in the sky. You can just place it on the ground, or wherever it is installed. It just looks upwards. It looks up into whatever is right above it. So that single patch in the sky. So there are pros and cons of this. The pro is that it will focus on one location in the sky, and you can do it night after night and add up the images to bring out very sharp and detailed images. So that's one thing. But you can't maneuver it and make it point at some other desired location in space. So it serves a certain purpose, and it's a good technology. Uh, so it's the world's largest liquid mirror telescope, and that's what we have right now. I think it's gone operational recently, and it's going to be a prototype for hopefully larger telescopes that will be made in the future. So in a liquid mirror telescope, there are certain restrictions. You can't make it larger than a certain size. I think the one that we have in Devasthal is about, it has a diameter of about 4 meters, if I'm not mistaken. Look it up. I think you try to make the telescope bigger than, let's say, 7-8 meters, there's gonna be problems because of the rotation of the Earth. There is something called a Coriolis force that will distort the mirror, and then you will not get proper images. The images will be distorted. So one solution is to go to the moon, which is much smaller, and therefore this effect will not really constrain us. So you could make a much larger mirror and install it on the moon. Of course, the problem is how to take it there. So in the future, one could be able to do that with large enough rockets, like what SpaceX is developing and all. So it could happen in the next 20, 30, 40 years. Yeah. And you could have a mirror on the dark side of the moon, let's say, the far side of the moon. And that could possibly give us very interesting astronomical data. So that is what it is, and that's what it's used for. It's used for looking at the night sky, a certain patch of the night sky that is right above it, and it can give very nice detailed images. So that's about the liquid mirror telescope in the Devasthal Observatory, North India. The next question is by Lokesh. In the context of your explanation in the 108th session, is mathematics pseudoscience or not scientific because it is definitive? If not, what does testability and falsifiability mean in mathematics? Right, so that is the question. That's the question. So, is mathematics pseudoscience? Because apparently there's no testability. So let's say I make a claim, a mathematical claim. I say that 1 + 1 is equal to 3. Can it be tested? Let's test it. This is 1. This is 1 pen. And I said that 1 + 1 equal to 3, right? Here's another pen. What do you see? I see 2 pens. So my hypothesis that 1 + 1 equal to 3 has been tested and falsified. So mathematics is testable. Mathematics is definitely falsifiable. And mathematics is all about proofs. Right? So we had the Pythagorean theorem, the triples, which you find in the Bodhyayana, Shulba Sutras. Even the Babylonians were aware of it. So that is something you can test. And if you give instead of saying that a squared plus b squared is equal to c squared, you say that a squared plus b squared equal to c cubed, you can test that out and you can show that is incorrect. It's not c cubed, it's c squared. You can test it out, and you can even prove or disprove theorems using logic, using the mathematical process. Entire proofs are constructed. So certain proofs take centuries. Take Fermat's last theorem, for instance. It was put forth by Pierre de Fermat in 1637, I think, in the 17th century. So it is not something that people started believing. It had to be proven. This guy, the mathematician Fermat, he made a certain claim in one of his notebooks or whatever. And then people were wondering whether this claim is true or not. And therefore, it had to be proven or disproven. And that process lasted more than 3 centuries. The attempt, the quest for a proof of this theorem. It's only in 1995 that the British mathematician Andrew Wiles was able to finally give a definitive proof that this theorem is correct. Right? And this entire process of trying to prove this theorem led to the development of algebraic number theory in the 19th century, in the 20th century. So you don't believe things blindly in mathematics. You have to prove it. Any claim, any mathematical claim that is made, any conjecture that's made, the Riemann conjecture or whatever, it has to be proven. Until it is proven, it is not, nobody believes it. It's something people are trying to prove or disprove. So you have to definitively prove that it's correct, that it stands, or you have to definitively prove mathematically that it is incorrect. So this is pure science. There is nothing pseudoscientific about mathematics. It is 100% testable and falsifiable. All right? So mathematics is the purest of all the sciences. Without mathematics, there's no other science. Without mathematics, there is no physics, because mathematics is the language of physics. Without physics, there's no chemistry. Without chemistry, there's no biology, and so on and so forth. So I hope that answers this question. The next question is by Akash. Which side are you on? Will AI, artificial intelligence, destroy humanity, as Elon Musk and a few other notable people say, or AI is extremely useful and can speed up the advancement of human technology far beyond anyone's imagination? Both scenarios are possible. So the question is, which one is more probable? See, AI is a technology. It's a certain class of technologies in which you have neural networks, quantum neural computing, all kinds of things, which all are now classified under the big umbrella of AI. So AI is a tool. A stick is a tool. You can use it for good purposes and for bad purposes. Yeah. Nuclear energy is a tool. It's a technology. It's a tool. You can use it to power the entire world and get rid of all the polluting technologies. You can also use it to destroy the planet with nuclear weapons. All technologies are merely tools. It all depends on how they are used. You can use them for good purposes as well as bad purposes. You can use them for good. You can use them for harm. Now, AI can certainly transform the world and make the world a better place. You can use machine learning to decrypt ancient languages that are yet ancient scripts that nobody has been able to decipher thus far. You can use AI, machine learning algorithms, etc., to develop new drug molecules to solve to cure cancer and whatnot. You can do all kinds of good using AI. You can use AI to monitor traffic and govern the way the traffic lights change, and that can give you a better experience in navigating the cities, for instance, and so much more. But AI can also be used for all kinds of bad purposes, for harm. It can be used to enslave humanity, essentially, using social media algorithms, using the dopamine releasing algorithms of likes and dislikes and shares and all that. Uh, so it has all kinds of uses. But the question is, who controls the AI? All the AI technologies that are currently being developed are mostly being developed in certain countries. Yeah. And even in those countries, let's take the United States, for instance, and China. Let's take two examples. There are more examples for sure. Let's take two examples. In China, who's developing the cutting edge AI technologies? It's the Chinese government and the Chinese military that's doing it. Now, when the government and the military is doing something, it has a certain purpose, a military purpose, a purpose that's about expanding your sphere of influence at the expense of the other nations. In the US, the US military and the government are for sure developing AI, and certain very large corporations are developing AI technologies. So it's typically the government, the military, and Silicon Valley. Now they will do it in order to benefit themselves. The large corporations will do it to get even larger, to make more money, to expand their revenues and the number of people who they influence and so on. So if it is used for good purposes, it can transform the world. But if it is used for making money and expanding your military influence, your military footprint, your geostrategic footprint, it's going to end up causing way more trouble than we can imagine. Right? So, on balance, I would be on the side of Elon Musk, that we need to be very, very, very careful about AI. It is very useful, but it can destroy humanity. It can possibly end up enslaving humanity. And AI doesn't have to become conscious to destroy humanity. AI doesn't have to become sentient, self-aware like they show in the Terminator movies. No. AI is already, it can do tasks at a level that's unimaginable for a human brain. So if you automate that, and if you have human beings controlling that, that gives those human beings almost unlimited power. and it's always for making more money. And you could call it enslavement. In the future, you could have actual enslavement without the enslaved people realizing they are enslaved, like in the Matrix movies and so on. So, on balance, considering the patterns of human history that I've been studying, we see some things over and over and over again. As new technologies emerge, they are always first used for military purposes, for the purpose of gaining more control, more power, and winning wars, waging wars. It's always that way. It's only later that those technologies produce spin-offs that are used in the civilian domain. So whatever we see of AI, there is a whole different AI that is not visible to us. That's being developed. That's about 20 or 30 years beyond what we can imagine. It's already that far ahead, and that is right now being developed by various militaries in the world. So eventually, if this continues like this, it could end up uh, enslaving humanity or possibly destroying humanity. Eventually, these AI systems, even if they are not sentient and self-aware, they could still, if you give them the wrong kind of decision-making ability, they could say that let's optimize everything, get rid of the human connection completely, and who knows what could happen. So I am on the side of Elon Musk and whichever other notable people there are, that it is a very dangerous development for us, and there needs to be restrictions and controls and checks and balances on the power that AI has, and essentially the people who are developing AI have. Yeah. Krishna Saraf says, have humans stopped natural selection evolution, and will overpopulation be our end? Okay, so lots of people ask me this question. Have we stopped evolving? Have humans stopped evolving? No, we have not stopped evolving. But we have to understand the time scales on which evolution is visible. Human beings, our species is called Homo sapiens, right? If you go back 250,000 years before today, you find skeletons, ancient skeletons of Homo sapiens in various parts of Africa, typically 2.5 lakh years before today. Those skeletons of Homo sapiens are anatomically and physically identical to ours. So those are called anatomically modern human beings. And that goes back about 2.5 lakh years before today. So in a quarter of a million years, we have not evolved noticeably. We are more or less the same. You go back a 500,000 years, you will see significant changes. You go back 1,000,000 years, you will see even more changes. You go back 3 million years, our ancestors were the same as the ancestors of the chimpanzees. You go back 5 million years ago, even the gorillas become 5 or 6 million years before today. Our ancestors and the chimpanzees ancestors and the gorillas ancestors were the same, right? So evolution happens over very long time scales. You don't evolve in 10 years or 100 years or 1,000 years or 100,000 years. Typically, the evolution, the process of evolution and the effects of evolution are visible over very long time scales, lakhs of years, hundreds of thousands of years, quarter of million years, maybe more. So we are evolving. We are certainly evolving, but we will not become a different species in the next 100,000 years, unless we mess up our genetics with various gene editing and other uh, experiments, right? So we have not stopped evolving. Evolution is still happening, but it's not visible. The effects are not visible. That takes a very long time to become apparent. The second question is, will overpopulation be our end? I don't think so. Right now, all the birth rates, the fertility rates in most of the countries in the world are declining. In Japan, it's way below replacement rate. In Russia, it's below the replacement rate. The replacement fertility rate is 2.1 children per woman. What I think it is. In India, it's now 2. So we are below replacement in India as well. Overall, right? In all the industrialized nations in Western Europe, etc., everywhere. In Turkey, in Iran, you have populations that have the entire national population that has fallen below the replacement rate. And then there are new viruses, etc., that are emerging. We are done with the previous one. Now it seems there's a new one coming up. So it looks like this is the decade of the virus, and they're going to keep on coming up with various incentives for human beings to stay locked down. and under lock and chain and that sort of thing. So I don't know. So I don't think we are going to uh, end up going far beyond the current population of the world. Yeah, in the very low income nations, the population is still rising. In Pakistan, I think the country is way above replacement rate. It's a very backward country. It's a very poor country. It's a very the literacy rate is very low, and typically there's a inverse correlation between literacy rate and the fertility rate. The higher the literacy percentage of a nation, the lower is the rate of fertility. In Pakistan, it's very low, and I think the number of children per woman is about four or more than four. But overall, if you look at the entire planet, the trend is downwards. So if this trend continues, we may even have a population crash in the next 100 years. So let's see how that goes. But it doesn't look like overpopulation will be our end. Hopefully, there's no end. Hopefully, we go on for the next few thousand years, and good future for humanity. I hope so. Swapnil says, it is now possible to bring extinct animals back through gene editing techniques. However, could there be a case wherein an animal that might be brought back from extinction may do more harm to the earth than good? If yes, was it worth it to have wiped out those animals in the past by humans from our planet in the first place? Okay, it is now possible. So the assumption that is made here, the assertion that's made here, is that it's now possible to bring extinct animals back through gene editing techniques. I'm not sure it's still possible. We are yet at that stage. I can't think of a single extinct animal that has been brought back thus far. We do have gene editing techniques. The technology is getting better every few years. We have something called CRISPR that you can use to edit individual genes inside a genome. And we do have we do have the technique of cloning. So we have cloned various animals, like Dolly the sheep and various other species. Perhaps, I hope it's not been done to humans, because that would be weird and unethical, most likely. So yeah, we have all this entire assortment of gene editing, etc. techniques, and I would say theoretically it would be possible to bring back, let's say, a mammoth back to life. A mammoth is an extinct species of elephant, and that species went extinct about 10,000 years before today. So the mammoths coexisted with humans. It's not too long ago. It's just 10,000 years. It's from an evolutionary perspective, it's yesterday. It's last evening, right? So, and we find preserved mammoths all the time in the permafrost in Siberia, in North America. Just recently, I saw on Twitter somebody discovered a baby mammoth that was perfectly preserved in the ice. Of course, its DNA would be available. Yeah, of course, it would be most likely possible to use the various genetic techniques to bring back, to give birth, to fertilize an egg with that sort of DNA. Yeah, or take a fertilized egg, modify its DNA profile, add the mammoth genetics into it, and then implant that fertilized egg into a female elephant, and that female elephant would most likely give birth to a live mammoth, which would bring the species back from extinction. It is possible. Nobody's done it thus far. For the past 20-30 years, Japanese scientists have been investigating that. I'm not sure how far that went, but I think it will be possible today. So if, let's say, we bring the mammoth back from extinction, let's say we bring the dodo back from extinction. These species lived until very recently. I don't think they would do any harm to the planet, right? So certain species, if you bring them back from extinction, they would just fit into the world properly, as long as these are species that lived until reasonably recently. The mammoth is a good example, about 10,000 years. Let's say you find a way of bringing dinosaurs back to life, like in the Jurassic Park movies. That would be out of place in today's world, because the non-avian dinosaurs were wiped out. They died out about 66 million years before today in the Chicxulub impact event. The avian dinosaurs survived. They are all around us. So let's say, what's happened recently. I don't know why this news has fallen off everyone's radar. A few years ago, people discovered a T-Rex bone, a femur, the thigh bone of a T-Rex. It was entombed, it was encased in rock. Yeah, it's like, I don't know how many million years old, or it is definitely more than 66 million years old. And for some reason, that rock broke, and what they discovered was tissue. You know, uh, it was liquid tissue with what looked like the remains of blood vessels, even blood cells, etc., inside the T-Rex fossil thigh bone, femur. Yeah. So if that survived all these millions of years, it is possible that you may be able to extract some DNA out of it. Now that has been hushed up, it looks like, and there were multiple cases of this sort of thing happening. So it is possible that DNA could be extracted from such fossils that still contain intact or near intact dinosaur tissue, right? And then even if some bits of the DNA are missing, you could. So the T-Rex was essentially a giant bird, right? The Tyrannosaurus Rex. It was a massive giant bird. Dinosaurs and birds are essentially the same thing. So you could use chicken DNA to fill in the gaps in the T-Rex genome, whatever the gaps, whatever is missing, and then you could try and recreate the species. It is possible that you may be able to, possible, maybe in the next 10, 20 years, you may be able to do that. You do that, will that species that you are recreating, will it fit back into the world like the mammoths would? The mammoths lived until recently. The world the dinosaurs lived in no longer exists. So that would possibly cause problems. What would they eat? Where would they fit into the evolutionary, into the environmental food chain, for instance? Right? Because they've been missing for 66 plus million years. So certain species, if you bring them back, would possibly not fit into the present ecological environmental scenario. They could possibly do more harm than good. There may be certain genetic aspects that could spread to other animals and cause problems. You know, if you look at the human genome, there's a lot of viral DNA in our genome, and we don't know why it's there, but it's there. And similarly, it's possible with dinosaurs and other species also. There could be some viral components to their DNA, to the genome. Now, could that cause problems if you bring it back and set it free in the environment? Possibly. So one has to be very careful when one is playing God. You cannot start playing God and start bringing extinct species to life without considering it very carefully. So that's what I have to say. You bring back certain species like recently extinct species to life again, it should not cause too many problems, hopefully. But you bring back older species to life, it could upset the ecological balance and cause problems. All right, this is by Amruta. Could you please explain what exactly is the precession of the equinoxes and why does it need exactly 26,000 years to complete? Also, there are many geological evidences that some sort of extreme calamity happens every 26,000 years, like earthquakes, floods, tsunamis. Is it related to the precession of the equinoxes? Okay, what is the precession of the equinox? The Earth is a spheroidal planet. You could approximate it to be a sphere. Yeah, it's oblate, it's squashed in a certain way, but it's nearly spherical. You could approximate it with a sphere. So, and it's a spinning object, right? So it spins around a certain axis. The axis is not straight up with respect to the plane of the solar system, it's tilted, right? And this tilt is spinning. So a picture is worth 10,000 words. Let me show you a picture, an image, so that you get what I am saying instead of me going on forever. So let's bring in the picture of that. Where is it? Here it is. Let me enlarge this a little bit. So this is our planet, the Earth. It is spinning around its axis. And this axis is tilted with respect to the ecliptic plane. All right? The plane of the solar system, you could consider it to be that. And there's a north pole and a south pole, which is, so you can see what that is. Now, let's take a look at another image. So the axis of precession itself goes around in this manner. And the North Pole right now is pointed at this star called Polaris. But 13,000 or so years ago, it was pointed at a different star called Vega, right? So 13,000 years ago, the North Pole, the polar star, the pole star was Vega, not Polaris. Today it is Polaris. And later it will be this star called Demeb and Alpha Draconis and all. So this phenomenon that you are seeing right here, is called the precession of the equinoxes, right? And this entire cycle, one entire cycle from Polaris to Vega and back, that takes about 26,000 years ago, 26,000 years, one entire cycle. It's actually about 25,700 or so years. You can say it's about 26,000 years. So that is called the precession of the equinoxes. Hopefully that makes sense once you see it in that manner, the image, right? So that's just how it is. In certain other planets, I'm sure it would take a different amount of time. All planets have a certain amount of tilt with respect to the plane of the solar system. And I'm not sure what the numbers are, but in other planets you would have a different amount of time that it takes for an entire cycle. So that's how it is. So that's why that's the amount of time it takes. Uh, there are geological evidences that some extreme calamity happens every 26,000 years. I'm not sure about that. You have cycles. There is something called the Bilkanovich cycle, that is a climate change cycle that you can look up, right? Um, there's another cycle or event that happens periodically in the earth, which is the reversal of the magnetic poles. So you have North Pole and South Pole. We also have magnetic poles in the earth, which are more or less aligned with the North Pole and South Pole. That also reverses in polarity every few, I don't know what the time period is. You can look that up if you're interested. So there are multiple cycles that are there that play out again and again and again in our planet, on our planet, and you see the events that are a consequence of that. So I am not sure if the precession of the equinoxes is related to any earthquakes or floods or tsunamis, but you have a variety of various climatic and other cycles that the planet witnesses on a regular basis. Mohak says, I want to ask what is meant by a light year. Okay, that's very simple. A light year is not a unit of time. It sounds like a year, right? Light year. It's not a unit of time, it's a unit of distance. So, light travels at a certain speed, roughly 300,000 kilometers per second. That's the speed of light. 300,000 kilometers per second. Yeah, I think that's what it is. Meters, kilometers, whatever it is. Look it up. Let me just speed of light. Speed of light. What is the speed of light? Meters per second. It's 299, 792, 458 meters per second. So it's about 300,000 kilometers per second. Uh, yeah, 300,000 kilometers per second. Okay, so that is the speed of light. In 1 second, it travels that distance, 300,000 or 3 lakh kilometers. Okay, in 1 second. So if you multiply that by 60, you will come up with the amount of distance light travels in a minute. You multiply that by 60, you will come with a bigger distance. It will give you a bigger distance. That's the amount of distance light travels in an hour. Multiply that by 24, you will get the amount of distance light travels in a day. Multiply that by 365, you will get the amount of distance light travels in 1 year. And that distance, whatever it is, calculate it, is called a light year. So that is a unit of distance, not time, right? So that, in short, is what a light year is. The amount of distance light travels in 1 year. That is a light year. And the closest star in our stellar neighborhood, Proxima Centauri, is roughly 4 light years away from here. So if you shine a beam of light, a torchlight in that direction, it'll take slightly more than 4 years for that light to reach that star, Proxima Centauri. So that's what a light year is. Okay, Atom Heart Mother. a Pink Floyd fan. The question is, yeah, Pink Floyd, great band. How far do you agree with the Big Bang theory? Is it even possible for us to predict how the universe would have started, provided that billions of years ago all physical laws could have been entirely different from the present ones? One question of mine would be that, is there anything in the universe having speed of more than light? Let's concentrate on the Big Bang. One question per person. So, how far do I agree with the Big Bang theory? It's not whether I agree or not. It makes sense. See, in science, in mathematics, in physics, you don't believe things. There is no belief. There's no I agree with this, I don't agree with this. This is not politics. It's not about opinions. It's about data. It's about facts. It's about evidence. So let's talk about the Big Bang theory. How did physicists come up with the Big Bang theory? It's not so that somebody. It's not like somebody dreamt it up and everybody said, "Okay, let's agree to this." It's not about consensus. How did this happen? So, in the 1920s, Edwin Hubble uh, came up with what's known as what he discovered. What Edwin Hubble discovered is that all galaxies are moving away from us. Okay, so he did a lot of meticulous calculations about, and how did he find out that galaxies are receding away from us? Because these galaxies are redshifted. When something goes further away because of the relativistic Doppler effect, the light that comes from that object is stretched out. When it's stretched out, it is shifted towards the red end of the spectrum. So there are certain elements that give off very characteristic wavelengths. You know what they are. When you look for that, you will find that it is shifted towards the red end of the spectrum. And the more it is shifted, the further away that thing is going away from us. And the further the speed is, the velocity is. So not only are galaxies and other distant objects going away from us, they are the movement is accelerating, which tells you that the universe itself is expanding. That is why the galaxies are receding further and further away from us. And the further you go, the faster they are moving away from us. Right? So Edwin Hubble came up with a certain value for what we now call the Hubble constant. Today we know it's about roughly 70 kilometers per second per megaparsec. Whoa, that is the value. So the first piece of the evidence is that the universe is expanding. There is unambiguous, incontrovertible evidence from observations, that the universe is expanding. Distant objects are moving away from us, and the more distant a galaxy or object is, the faster it is receding from us. So the universe is expanding, and the expansion is accelerating the further you go away. So now, let's say you reverse the time. If it is expanding away from us, in the past, those objects would have been much closer to us. And based on the speed of the expansion and all those things, if you do proper detailed calculations, you will find that if you go back about 13.7, 13.8 billion years before today, the entire universe would have been compressed into a single point. Right? It's clear. You just have to take the expansion backwards in time, and you can come up with the approximate time when the universe was born. Right? So that is one thing. There is no doubt about the fact that the universe is expanding, and the expansion is accelerating. Secondly, so it was clear that the universe would have started as a single point, or something very close to a point. Then people understood that if everything was concentrated into a point, it would have been just pure energy, incredibly dense energy, right? And then the expansion happened, which Fred Hoyle called the Big Bang. So if such an event happened, there would have been an immense amount of radiation in the past. And as the universe expanded and cooled, that primordial radiation also would have cooled down and stretched out over time. It would also have been redshifted over time. Very clear. And if that happened, then that radiation would still be present in the universe today. And if you know how to detect it at the appropriate wavelengths, you should be able to find it. So until the 1950s or so, people did not quite agree with this theory, this Big Bang theory. They said it is like creationism. The Christian creation doctrine that God created the universe and all that. So they said that the universe should be a steady state universe. There is no God in all in science, and you're trying to recreate Christian theology and so on. The Christian theology says that the universe was born about 4,000 years ago. In physical cosmology, the calculations were about 13, uh, came to an answer of about 13 point something billion years, or whatever the initial calculations were. So most physicists at that time did not believe in this ridiculous idea of a big bang. Fred Hoyle even gave it the name Big Bang just to make fun of it, but that caught on in the media. So that's why it's called the Big Bang theory. It's not a bang, it's not an explosion, it's an expansion. But then what happened is that this cosmic microwave background radiation was discovered by Penzias and Wilson, I think. I think. So they discovered this relic radiation, the leftover radiation that can only have come from this Big Bang event. And over time, we have mapped this radiation out. It's very, very uniform, but over very large scales, you find anisotropies and fluctuations in the levels and all that, right? So you have the Planck satellite, then the WMAP satellite, which has given us a very detailed map of the background, the relic radiation of the universe, and so on. So because we have the evidence of the expansion of the universe, the accelerating expansion of the universe, and because we have this telltale clue uh, of the microwave background radiation, the CMBR. These and we have lots of other data points that I will not go into. Because of all these data points, it is clear that this event actually happened. So it's not about belief. Nobody believed it until they found the evidence. You get it? Science is not about belief. It's not about agreeing with this or agreeing with that. You look at the evidence, you use the tools of science, the scientific method, and if the evidence agrees with the theory, then the theory is likely to be correct. Even today, the so-called Big Bang theory is not perfect. It doesn't explain why this happened. It is only a chronological history of the universe. What the Big Bang theory, the Big Bang model, the lambda CDM cosmological model, what it does is it attempts to recreate the chronology, the chronological history of the universe. It is unable to explain why things happened. What caused the Big Bang? We still don't have the answer. We are trying to figure it out. And there are lots of uncertainties. The very initial moments after the Big Bang, we don't know anything about it, more or less. Yeah. The inflationary epoch, the reheating epoch, we have recreated much of it based on observational evidence. So I am very clear about this. All scientists, physicists, cosmologists are clear about this. The best theory that we have today about the origin, about the history of the universe, is what we call the Big Bang theory, right? So based on all of these things, we can actually uncover roughly what happened and possibly predict what will happen in the future, right? So that's how it is. So that is my answer to that question. Right. The next question is by Lakshya. I read Neil deGrasse Tyson's book, which says that wherein he says that the accelerated expansion of the universe will, in 22 billion years in the future, end in what's called the Big Rip, when even atoms get ripped apart. Would this really happen? Okay, so the Big Rip, there are multiple possible scenarios about the future of the universe. One is that the universe, we know it's expanding. The expansion is accelerating by something which we call dark energy. We don't quite know what it is, but we believe that we know something called dark energy exists. We don't know what it is. It seems to be some kind of fluid, some kind of repulsive force, whatever it is. We don't know what it is. It's there. So one scenario is that the universe will keep expanding. The acceleration will get the expansion will accelerate more and more. Eventually, the observable universe will just be our galaxy and nothing else. Eventually, even that will fly apart, and that's called the Big Rip. Eventually, even the atoms uh, atoms will be ripped apart, even space time itself will be ripped apart. That's called the big rip. Another scenario is that after a certain period of expansion, the universe will start contracting and there will be a big crunch. And will it go, and we will have the reverse of the big bang in that scenario. There is something called the big bounce model, in which there will be a big crunch, then again expansion, then again a contraction. It's a cyclic process, a cyclical universe. And there are various other models as well. So whether the big rip happens or not depends on the type of dark energy we have in our universe. So if the dark energy in the universe increases without limit, it would certainly overcome all the forces that hold the universe together. The big force that holds large scale structure together is the force of gravitation, which is geometrodynamics. It's the general relativity, right? It's governed by what we call general relativity. So the time to this hypothetical big rip, how far in the future could it happen? It depends on a number of on a number of parameters. The first is the equation of state parameter, which is called W, or W typically, which is the ratio between the dark energy pressure and the energy density. So if dark energy is a fluid, let's say you have a fluid, a liquid in a glass, in a vessel. So that this fluid will have a certain pressure, it will have a certain density. If dark energy is a fluid of some kind, it will have a certain pressure and a certain energy density. The ratio of these two quantities is called the equation of state parameter, which is denoted by W. The second parameter is the Hubble constant. There are two possible values of the Hubble constant: 67.7 kilometers per second per megaparsec, or 73 kilometers per second per megaparsec. That's the Hubble tension. So that's the Hubble constant. The third parameter is the density of all the matter in the universe, which is called omega m. So if you take the value of W to be minus 1.5, if you take the Hubble constant to be about 70, and the density of all the matter in the universe to be about 0.3, then I believe you come up with a time to a future big rip to be around 22 billion years from the present day. If you take a different value of W, for instance, which we don't quite know yet, so if you take a different value, it you could get a different time for the big rip. If you take a value of W less than a certain value, then you may never have a big rip, and you will have a big crunch. So it depends on what values you take in this calculation. So we don't quite know yet. It is possible there could be a big rip, depending on the values, and the values are something that we don't have a lot of clarity about as of today. So it could happen, it may not happen, we don't quite know. So I haven't read the book that you're referring to. He has a number of books. Very good author, obviously. Very famous and beloved astrophysicist, the people's astrophysicist. So yeah, I'm sure that he must have come up with one of these calculations, and according to one of these scenarios, you could have a big rip in about 22 billion years. So what would a big rip look like? First, all the neighboring galaxies would disappear. They would go far away, and they would be beyond the observational range. Then even our galaxy will be pulled apart. The force of gravity will be defeated by the expansion of the universe. Eventually, even the solar system will be pulled apart. The planets will fly off. The Earth will fly off somewhere. Then eventually, the atoms and molecules will all dissociate. The subatomic particles will fly off from the atoms, and in the end stage, even space-time itself will be ripped apart. So that is what a big rip would look like. Not a nice thing, but hey, it's too far away in the future if it ever happens. So that is about the big rip. Ashay says, how does fire cast a shadow? Yeah, fire can cast a shadow in certain scenarios. So what is fire? Fire is what comes out from combustion. It's a lot of heat. Inside, what is inside a flame? The light that you see comes from the combustion of various particles and various substances. And because it is hot, it rises upwards. That's why the flame is always pointing upwards, typically, unless there is wind. And inside a flame, you have certain kinds of particulate matter, soot, perhaps from a candle, or the whatever substance has been combusted, the carbon particles, or whatever it is, right? Soot is also carbon. and it goes upwards. It rises upwards because the surrounding air is cooler than the flame. Now, not all flames cast shadows. If you're in a dark room and you light a flame, it will actually give off light. It won't cast a shadow. So, in what scenarios will you have a flame casting a shadow? One scenario is that you have a flame. Let's say you have a candle, a candlestick, a flame on the top, and you shine a very bright light from behind it towards the wall. So, you have a flame here, you have a wall here, and here you have a very bright light, which is brighter than the flame itself. In that case, the flame will cast a shadow because it is obstructing the path of this brighter light. So that is one scenario in which a flame could cast a shadow. There's another scenario. So a flame, like I said, it's a very hot substance. It warps the air and it ends up causing a phenomenon called optical refraction. A refraction happens when there is a boundary between two substances, which through which light passes, a thicker substance and a thinner substance, different temperatures or whatever. And it's this is the phenomenon in which you, if you put your finger in a glass of water, your finger appears to be broken or bent, or a pen or a stick or whatever. So that also happens at the interface of a hot flame and cooler air. So it kind of warps and distorts the path of light, and that also can appear to cast a shadow. It's an illusion. In this case, it's an illusion caused by refraction of light. So two scenarios: one in which a flame obstructs a much brighter light, and secondly, a flame which causes refraction of light, which appears in the form of a shadow. So these are two scenarios I can think of right now. Okay. Okay, Saurabh says, why is there more matter than antimatter? That's essentially an age-old mystery. So, matter, antimatter. What is antimatter? So, antimatter particles share the same mass as your regular matter particles, their matter counterparts. But these antimatter particles have qualities that are opposite. Like electric charge is a very good example. So, we have subatomic particles like the electron, like the proton, etc. Their antimatter counterparts exist. For the electron, as you know, is a negatively charged particle. Its antimatter counterpart is the positron, which has the same mass, but it has a positive charge. The proton, as you know, is a positively charged particle. Its antimatter counterpart is the antiproton, which has the same mass, but a negative charge. The photon of light is its own antiparticle, and so on and so forth, right? So the very early universe, right after the Big Bang, was pure energy, just pure energy. Now we know from quantum field theory that vacuum is not quite empty. It is teeming with particle-antiparticle pairs. So from because of the Heisenberg uncertainty principle, that's a whole different story. But these are virtual particle-antiparticle pairs that are formed, and they recombine very rapidly. So that's vacuum energy, right? So in the very early universe, when you had pure energy, eventually what happened is that it gave rise to incredible amounts of particle-antiparticle pairs with the relation of E equal to mc squared. And these particle-antiparticle pairs would form and and recombine and give back energy again. And if you look at see, whenever we create matter in particle accelerators, we typically get, and we not typically, we always get an equal amount of matter and antimatter, right? But in the early universe, for some reason, even though all of these particle-antiparticle pairs should have recombined and just given off pure energy, what happened is that in the very early universe, approximately one particle per billion managed to survive, and there was an excess of matter over antimatter for whatever reason. We don't know what it is. Some unknown mechanism or law of physics, or we don't know what it is, caused this to happen. A slight majority of matter as compared to the antimatter that was produced. We don't know why this happened. We don't have the answer. One of the hypothetical scenarios is that possibly our universe has an antimatter counterpart. So from the Big Bang, not one universe came out, but two universes came out. one with more matter, one with more antimatter. And today you have two parallel universes that have come out of the Big Bang. One has matter, and one has antimatter. And eventually, when the two recombine in the future, big crunch or whatever, it will all go back to pure energy. That is one hypothesis. It's not a theory; it's a hypothesis because it is not testable or falsifiable. So we don't quite know why there is more matter than antimatter. Maybe some unknown law of physics exists. Maybe some unknown mechanism caused this to happen. Maybe we have two universes, one with matter, one with antimatter. We don't know. This is called baryon asymmetry, and this is something physicists are actively trying to understand why it is so. As of today, we don't quite have the answer. Hackeristic says, why do we say that heat can travel through vacuum? While heat is the kinetic energy of atoms, and radiation itself is just electromagnetic radiation, which to be generated doesn't necessarily require heat. I don't say that heat travels through vacuum. I don't know who says that. I'm sure people say that. People say all kinds of things. What travels through vacuum is radiation, electromagnetic radiation, like you say. There are other forms of radiation as well. There is actually something called gravitational radiation, gravitational waves. So what happens? Let's take the case of the sun. We look at the sun. When the sun rises, we feel hot, right? We feel the heat. So people say that the sun is all these 8 light minutes away. Yeah. And yet, from that far away, it's giving us heat. That's what we sense. That's what we feel. What really happens is that the sun gives off electromagnetic radiation in the form of photons, light waves. Photons, wave particle duality. Photons or light waves. These photons or these light waves, whatever you want to call it, they carry a certain amount of energy, right? E equals h nu, in case you know. So based on the frequency of the light, there is a certain amount of energy associated with it. This energy, this radiation, travels through vacuum. It's just radiation. It's just bundles of energy. Once these photons, once this radiation reaches the earth, it interacts with the molecules in the atmosphere, goes through that, it heats up the atmosphere, right? Because molecules absorb this energy, they vibrate, and they give off something that we perceive as heat. Similarly, much of this radiation makes its way through the atmosphere, and it's incident on our body, on our skin, on rocks, on vegetation, etc. And all of these atoms and molecules absorb the energy, give it off in certain wavelengths, and also give off infrared radiation that we perceive as as light. So that is how the process roughly, I'm giving you a very rough outline of what happens. Yeah. But that's how it is. So it's not heat that's traveling in the vacuum of space. It is photons. It is electromagnetic radiation that's traveling. And when it reaches the planet Earth and it reaches us, that's when it interacts with the atmosphere and all the substances on the planet and gives off what we call heat. Okay, Karan says, what was the purpose of digging the Kola super deep borehole? So the Kola super deep borehole is something that was dug in the 20th century in the USSR. A very deep borehole, a very deep hole in the surface of the earth. I think it reached a depth of more than 12 kilometers. And it's the deepest hole that's ever been dug anywhere in the world. Right? What is the purpose? To figure out what the earth's crust is like and what properties it has as we go further deep inside. Find out what's inside, how it is inside. Curiosity, scientific curiosity. And of course, it will have certain applications. So they found certain interesting phenomena as they went deeper. As you go deeper, the temperature increases. As you know, deep below the Earth's surface and mantle, you have a magma layer, which is all molten rock. So as you go deeper into the Earth's crust, as you go deeper below the Earth's surface, the temperature increases. It gets hotter and hotter. So I think around a depth of 10 or 12 kilometers, the temperature was, I think, more than 200 degrees Celsius, possibly something like that. Look it up if you want. So that's one thing they found. They also found lots of hydrogen in there, hydrogen gas. They also found that the rock doesn't quite behave from a straight from the exactly the way it was predicted. There's a different kind of um, physics of the rock, metamorphic rock or whatever. I'm not sure what it is. At those temperatures and pressures, the rock behaves like a plastic at a certain depth, and that made it impossible to drill further. So they found a number of interesting things, and it helped us understand the geology and the physics of the Earth's crust more better. Yeah. So yeah, so we found some interesting data from this experiment, and eventually I think the project ran out of funding, and that's why it was stopped. So the purpose to dig this borehole was to understand our planet better, and that's certainly what happened. Avinash says, how did life evolve from non-living matter? And Swapnil says, can you please explain the Miller-Urey experiment which gave rise to the field of prebiotic chemistry? Okay, so these two questions are interrelated. It's about life. It's called abiogenesis, the chemical origin of life, the emergence of life possibly from non-living matter, right? So this experiment was done in the US in the 1950s. Two guys, Miller and Urey, I believe. So what they were doing, they were testing the possible chemical origin of life. So we know that the Earth formed about 4.5 billion years before today, roughly, and it was a very different place at that time. It was a very hot ball of extremely hot molten rock and all. There was a lot of volcanism. The composition of the atmosphere was very different from what it is today. There was a lot of lightning and so on and so forth. So they tried to recreate that environment in this experimental apparatus, right? So what they did was they took a flask with methane, CH4, ammonia, NH3, and hydrogen, which is H2, and a different flask with water, which is H2O. They interlink the two, and they heated the water to create vapor, steam, and they also had a spark plug in there, which would create electrical sparks all the time to recreate the lightning scenario of the early Earth. And they let this run for a certain period of time. And what they found is that a number of amino acids were formed from this procedure. I don't know how long the experiment ran, maybe, I don't know, a week or so. I'm not sure. Look it up. It ran for a certain amount of time. And these very simple ingredients that they started off with eventually formed a number of amino acids. Amino acids. So these are organic compounds that are the building block of life. Amino acids give rise to proteins. Proteins is what we have in our body. It's the foundation of all life on the planet. So I think what they found at the time was 5 or so amino acids, but later on, many decades later, when it was reanalyzed, they found well over 20 different amino acids. So that's what the experiment was. I'm sure we can look it up, and let me see what the apparatus looks like. Uh, Miller-Urey experiment. Let me share the screen. So what did this apparatus look like? Yeah, so this is the experimental apparatus that they had. There is one flask with water, methane, ammonia, and hydrogen, and a different a different flask which is connected to this, which has boiling water on a heat source. It's giving off water vapor, and there is an arrangement for creating an electrical spark. And you run this for a certain amount of time, and then what you get is all of these amino acids that emerge out of this experiment. So that, in brief, is the Miller-Urey experiment. And yeah, that is one potential way in which life or the building blocks of life could have emerged in the very early Earth. This is abiogenesis, prebiotic chemistry, and so on. So that is possibly one scenario in which life evolved from non-living matter. Could this, if you keep it going, could it give rise to DNA molecules? We don't know. I don't think anybody's been able to successfully induce the creation of DNA or RNA molecules in such an experiment? So that is one mystery, because all life on Earth, it does come out of these building blocks, amino acids, etc. But all life on Earth, whether it is the most complex organisms like human beings and apes and whales and all that, or whether it is the dinosaurs, the lizards, or even if you go down to the microscopic level, bacteria, viruses, whatever you have, all life on Earth has DNA, right? So where did this DNA come from? That's the main big real question. So there is this panspermia theory, which says that DNA came from outer space. Because when we analyze various uh, meteorite samples, rocks that have fallen from the sky in the form of meteorites, we often find signatures of life on these meteorites. You know, organic compounds, maybe even, I'm not sure if they have found amino acids, but possibly, yeah. So we know that there is a lot of water on various comets. We know that there are organic compounds in these comets and asteroids. It is possible that something else may also be have been there in the past. Who knows? So there is one theory, but there is no evidence for this theory, the panspermia theory, that life came from outer space. But it is a possibility. So we don't quite know as of today. We don't quite have the answers. How did life evolve from non-living matter? One possible answer is the Miller-Urey experiment, but it doesn't answer the question of the DNA. Where did DNA come from? Where did that emerge from? So as of today, we have more questions than answers, but it's good. It means there is a lot of scope for further research and progress. Alpha Beta says, do do satellites have a specific lifetime, and on what factors does that depend? What causes satellites to hit the Earth? They are orbiting around the Earth without any fuel, getting solar energy. Okay. Why? Okay. Do satellites have a specific lifetime? Yes. It depends on a number of factors. First of all, the components of the satellite, the machinery of the satellite, how long will it last? Everything degrades in vacuum, in space. Even on Earth, any machine won't last forever. After a certain time, the components will wear out and will stop functioning. So there is a certain amount of time anything can work, and then it stops working. Let's say you have a satellite with a fuel source. Uh, that fuel source will have a finite lifetime, after which the electricity will stop flowing. Sometimes some satellites don't have any fuel source, energy source. They have solar panels. Even those solar panels over a few years will slowly degrade. The amount of energy they will be able to give the satellite will slowly decrease over time. Eventually, over that, even that ends, and the satellite ceases to function the way it's designed to function. That is one factor. So if you have a satellite that's, let's say, at a geostationary orbit 36,000 or so kilometers above the surface of the planet, then that satellite will have a finite lifetime, after which it will not last, because of these factors which I just outlined. There is another uh, factor that limits the lifetime of satellites. When you have satellites in low Earth orbit, let's say 200 kilometers above the surface, let's say 300 kilometers above the surface, these satellites will experience something called atmospheric drag. So technically, the atmosphere ends at 100 kilometers above the surface of the planet. That's technically, because actually it doesn't quite end there. The atmosphere just goes on and on for a very long, until it becomes so diffused you can't really differentiate the atmosphere from outer space. But it doesn't abruptly end at 100 kilometers above the surface. So even if a satellite is 200 kilometers above the Earth's surface, it will experience collisions with atmosphere molecules, air molecules. The collisions will be very rare, very infrequent, but they will be there. So this gives rise to something called atmospheric drag, which slowly over the days, weeks, months, years slows down the velocity, slows down the speed at which the satellite is orbiting the Earth, and because of that, the altitude of the satellite comes down slowly, slowly, slowly. And the further and the closer it comes to the surface of the Earth, the higher is the atmospheric drag. So it's a self-reinforcing phenomenon. And once the satellite is low enough and the atmospheric drag is high enough, the satellite will break apart and burn up in the atmosphere. So some satellites have a rocket engine, small rocket engine, which will periodically be used to boost the orbit of the satellite. But even that rocket fuel will eventually end, will get over, right? So these are the factors that limit the lifetime of a satellite. If it's a low Earth orbit satellite, it will eventually end up re entering the atmosphere and burning up, hopefully, not hitting the planet. So that's what happens. Tejas says, how many years will it take for us to mine other planets? How will it change our world as raw materials for industry will become cheaper? So the first question is, how long will it take for us to reach another planet? That's the first question. And we are not talking about the moon or asteroids, we're talking about other planets. So the only other planet that is a viable candidate for us to go to as of today in the 21st century is Mars. It's our closest neighbor. It takes between 9 months to slightly more than a year, depending on the time of the year, to reach there if you have a good enough rocket. And so, when do we expect human beings to reach there? Right now, we have a few robots on the planet. NASA has a couple of robots, at least one robot, if I can recall, which is currently active and operational. There's a small helicopter like drone also that's active on the planet right now. And there are a few satellites, robot satellites in orbit, including our own Mangalyaan, which is still operational. So as of today, we are in a position to send robots to the planet with great difficulty. These robots are very rudimentary machines. They are not in a condition, they are not capable of mining the planet. It is expected that the first human trips to Mars will begin in the 2030s, most likely. And possibly it will be SpaceX or NASA that will be at the forefront of that. We already have the technology for that, but it is still very risky. We could possibly send humans there, or maybe they could die on the way, or maybe we could not be able to bring them back. So we need a little more technological progress. We need to make this entire process as low risk as possible, because human lives are precious. So most likely in the 2030s, human beings will reach Mars. And if there's a big enough rocket like the SpaceX, the biggest one they have, you could transport all kinds of machinery there, including mining machinery. So at the earliest, within the next 20 years, you could have the first attempts by humans to do some kind of mining on Mars. Typically, it will begin with trying to chemically alter the soil in order to produce food there or something, and possibly produce oxygen and water from the soil of Mars. It will begin like that, but eventually we will start drilling deep into the crust of the planet, and possibly extract minerals, metals, or whatever else is of value. So the first human habitation will most likely happen within the next 20 years, and another 10, 20, 30 years, and you could have some mining activities happening on that planet as the human settlement possibly grows there, right? So possibly, hypothetically, in the next 50 years, you would have some mining activity on Mars. But what would that mining activity be done for? It would be done in order to create a proper sustainable habitat on that planet. Let's say you want to build a larger Mars base for permanent human settlement. You would need materials. You would try and extract those materials out of the planet itself instead of transporting them all the way from Earth, because it takes a lot of energy to transport even 1 kilo of any material from Earth to Mars. So the first attempts at mining would be in order to create a more sustainable living environment right there, not for bringing materials back to Earth. So I think the first 100 or so years, 200 years possibly, whatever mining happens on Mars would be for creating and expanding a human settlement, not for bringing anything back to Earth. Eventually, possibly, perhaps, you may have some materials which are valuable on Earth, which could be transported from Mars to Earth, maybe from some asteroids to Earth, possibly. But there will be a very high cost for the transportation to happen. So I'm not sure if it will really change our world and transform our raw materials industry. Eventually, if things go well, you could have permanent human settlements on Mars and industries which possibly target certain asteroids. So that sort of thing could happen in the next 200-300 years. So that's how I envisage this as going. Initially, the human settlement on Mars will be a very small scale thing. It'll be tough for them to survive, and they will try to expand that settlement and make it more future proof. So that's how I see it going. Human settlements will happen over the next 30 to 100 years, and mining will proceed from beyond that at any sustainable level. That's how I see it. Let's see. Okay, Flying Raven says, some time ago I heard about a discovery of a white hole. What's a white hole? What are the properties of a white hole? A white hole is just like a black hole, but it's like a time reversed black hole. So in a black hole, you have an event horizon, and whatever crosses the event horizon is gone forever, essentially, from a classical general relativity perspective. So in a black hole, everything goes inwards typically. In a white hole, it's like you have the time reversal of a black hole. Everything comes out of a white hole. Nothing can ever go in. A white hole also has an event horizon, and that is the point at which nothing can cross into the white hole. So a white hole would have similar gravitational properties like a black hole, but from time to time it would throw out material from within itself, and possibly it could get smaller, possibly, right? So there are certain solutions of the Einstein equations that give you white hole solutions, white holes. So that's what a white hole is. We have never ever discovered one. I'm not sure where you heard about the discovery of a white hole, but yeah, we don't know if we have ever discovered one. If there is a white hole somewhere, it would look from far away just like a black hole. There are certain black holes that are very massive, supermassive black holes. Most galaxies have a supermassive black hole at their center. Some of these are active galactic nuclei, which give off these massive, giant jets of radiation and material, right? Because of the accretion disk that is around the black hole. So maybe these could be white holes that are giving off these jets and material coming out of that. So we can't quite tell from far away whether what we are seeing is a white hole or a black hole. From afar, it looks more or less the same. If it's an isolated white hole, we could be able to tell perhaps that it's a white hole and not a black hole. But we are so far away, and these objects are typically found at the center of galaxies, which are at enormous distances away from here, millions of light years from here. So we can't quite tell. But from the theoretical perspective, from the perspective of general relativity, white holes should exist, could exist. But we have never discovered one. But to make it very simple, a white hole is like a time reversed black hole. In a black hole, everything goes inside. In a white hole, everything goes outside. Both have an event horizon, which is the boundary of no return. So that is what a white hole is in very, very brief. Okay, Sauraj says, why is ISRO not making reusable rockets? Why do we have such tiny rockets with very little payload capacity? When will ISRO come out of its space taxi program? Is it a money problem or something else? Can we wait till the time India reaches $10 trillion of its GDP? Don't you think if we wait, we'll be left behind in the space race? I think we need to start taking ISRO forward. For the longest time, we have a couple of rockets, the GSLV and the PSLV. The PSLV is the workhorse, which is actually a rocket with a very small payload capacity. It only reaches polar orbits. The GSLV is designed to reach geostationary orbits, 36,000 or so kilometers above the surface. But even that is not a very powerful rocket. It's the most powerful one we have. It's not very powerful when we compare it with other space programs and other rockets that other countries have. So why are we not taking it forward? Our rocket engineers, we call them rocket scientists, are very much capable of building more powerful rockets. Very easy. We have the technology to do that. We have the know-how for doing that. It's all about the funding, the finances. You get a higher budget, and if you get the go-ahead from whoever is in the decision-making capability, then this will happen. It can happen very rapidly. We could have a way more powerful rocket in the next 5 or 10 years if we give the go-ahead and we give the right amount of money. And why are we not making reusable rockets? I don't understand why. SpaceX has been doing it for like close to a decade now, if not more. If a private company can do it, why can't ISRO do it with the government support and all that? So it's all about political will, I would say. So I'm not sure why it's not happening. I would like to see ISRO go ahead of its competitors. We have the money. Why don't we fund ISRO and give the scientists the go ahead to explore everything that everybody else is doing and go ahead of the competitors? We have the ability. We have the ability to go ahead of China, of Japan, even SpaceX in the next 10, 20 years, if the funding is made available and if the scientists are given the right directions and the permission to go ahead. So I don't know why it's not happening. I would like to see it happen. I've been saying this for a very long time. If we wait for 20 years, we will be left a long way behind our competitors. So I hope something is done about this. Naman says, what is relativistic speed? When two particles of a certain mass are moving at, let's say, 99.99% the speed of light, anti-parallel to each other, which means in this direction coming towards each other, the relative speed shall be more than the speed of light. Are you sure? So the question is, how does relativistic speed justify Einstein's special theory of relativity? You need to study Einstein's special theory of relativity, Lorentz transformations, relativistic velocity addition, all that, and you will see it's not the case. Even if two particles are moving at the speed of light, if two photons are moving towards each other at the speed of light, so this guy is at the speed of light, this guy is at the speed of light, and if I'm sitting here, I will see the other guy coming to me not at twice the speed of light, but only at the speed of light. That's how velocity addition happens in special relativity. So let me show you how this works. Let me demonstrate what it is. Let me share my screen. 1 second. Give me a second. And I will actually try and demonstrate this. So to understand this, I cannot explain this to you in a way that makes sense intuitively. Relativity doesn't make intuitive sense. Quantum mechanics doesn't make sense from an intuitive perspective. So let's talk about the velocity addition. So this is the formula that governs velocity addition. We are applying the Lorentz transformations to the velocities, right? So you have something that's coming in one direction at 0.8 times the speed of light, and the other one is coming at 0.9 times the speed of light. And then yet when you add it up, it doesn't add up to 1.6 times the speed of light. So let's go to basic application. Okay. So relativistic relative velocity. There is VA and VB in two different directions. Let's say you are saying that VA is 0.99 times the speed of light. I am entering that. And VB in the opposite direction is minus 0.99 times the speed of light. Then what you get is 0.999999494, whatever, C. It doesn't add up to 1.8 or whatever times the speed of light. It does not. It adds up to less than the speed of light, even though both are almost at the speed of light. So that's how it works. You have to study the equations. You have to study the theory, and then you will realize it's not quite the case. So you can look it up. The mathematics is quite simple, actually, compared to the general relativity mathematics. So that's how it works. So to understand how these things work, you have to actually study the physics, study the math. I can tell you, but you won't believe it most likely because it doesn't make sense to you. So unless you go deep into the physics and you actually study the equations and how they are constructed, how they are derived, only then will you understand. But that's how it works. The cosmic speed limit is the speed of light. Nothing can travel faster than the speed of light. And if a particle has mass, it cannot even reach the speed of light. It will always be below the speed of light. And there are all these relativistic effects like time dilation and so on and so forth when it comes to these phenomena. Okay, let's take one more question. Marcus says, is a plant-based or vegan diet healthier than a diet that includes animal products? Does dairy and meat cause cancer? There are many controversial opinions among scientists floating online. Is there any reliable scientific evidence from either side? What's your take on this? There seems to be a very clear correlation between red meat, high consumption of red meat, and cancer. The problem with these studies is that most of these studies, if not all of them, are sponsored by various corporations. In the 1960s in the US, doctors used to say that uh, doctors used to advertise their favorite brand of tobacco, of cigarette, Camel, and so on. You can see the ads online. Even today, you can see that on Google if you do a Google search. So doctors and the medical industry have, for the longest time in the West, in the US, been co-opted and paid to push out propaganda. And today, even today, you have the meat industry hiring doctors and paying them to come up with various studies which are published in medical journals, scientific journals. We don't quite know how accurate these studies are and how true they are. It's always possible to fudge the data, to cherry pick certain cases and ignore certain cases. So we don't know. There are so many opinions among scientists. But what seems to be the case from my perspective is that the more vegetables you eat, the healthier you are. And the less meat you eat, the healthier you are. Of course, you need protein. You can consume more dairy or more legumes to get your protein. You can get your full protein profile that you need for a day from a completely plant-based diet that has been more or less proven now, right? The meat industry disagrees with that. They will have scientists who will say that you will not get your complete protein profile, your full protein profile, only from eating legumes and vegetable and plant products. You need some meat or dairy. Typically meat. They'll push meat. That's not quite the case. So from my perspective, from everything I've read and studied over the decades, my perspective is that if you minimize your intake of red meat or meat, and if you maximize the amount of plant based food you eat, you're going to be healthy. The more plants you eat, the more plant based food you eat, the healthier you are. And that's something I think most studies do bear up with. They do show that. So my opinion, it's again an opinion. I have not done actual research on this. I've only read lots of research about this. So from all I've read, this is what I feel. This is what I have concluded. You need to eat lots of plant-based food. If you are a meat eater, try and eat more white meat and minimize the amount of red meat that you eat. And dairy would be actually better because dairy can give you all the protein you need. Dairy doesn't seem to cause cancer. Red meat seems to cause cancer, right? So that's what makes sense to me from my perspective, right? Right. Okay. Let me take about 5 minutes of questions from the live chat. In case you have questions for me that you would like to ask me right now in the live chat, this is the time. I'll take a few questions. Let's. Mm, okay, this is by Samhita. What is actually about the planet 9 that has recently been discovered? We have not discovered planet 9 yet. Pluto used to be planet 9. Now they have reclassified it as a minor planet or whatever else they call it. I don't know what they call it nowadays. I don't care. For me, I grew up considering Pluto as planet 9, and that's what I call it. Now, there is news about the possible existence of an unknown planet out in the far reaches of the solar system. It is possible. It may even be likely. How do we come up with these these scenarios? It's because we can infer the presence of a massive object at a certain distance from the sun based on the kind of orbital effect it would have on smaller planets, minor planets, etc. So there are multiple objects in the solar system that have been discovered that have very strange orbits, and that can only be caused, or most likely be caused, by the presence of an unknown massive and large object at a certain distance from the sun. So this pattern that astronomers have observed, they've discovered lots of planets over the past 20 years that exhibit this strange orbital uh, path. So it looks like there is something out there that has caused these minor planets and other Kuiper belt objects to acquire these weird tilted etc. Orbits. So there seems to be something out there, a massive planet which is currently very dark, which is not visible. Maybe a planet that is multiple times the size of the Earth from the mass perspective. So there could be something out there. And that's what the search is on for. Some people say there could even be a black hole orbiting the sun that we are not aware of. You know, if it's a black hole, it's dark, and if it's so far away, it's not going to do any mischief. Like the kind of mischief black holes cause in science fiction. No, a black hole out there in orbit around the sun could maybe it's a primordial class black hole. Smaller than the sun, so it doesn't have massive gravitational effects, and it's still sitting out there. So that is also a possibility. So maybe our planet 9 could be a hidden black hole in our stellar backyard. So it's not been discovered. Everyone is searching for it. There is a certain amount of likelihood that it may exist. And let's see what time tells us. It would be interesting. It would be fascinating to discover a large planet hidden somewhere far away from the sun, but it's orbiting the sun. That would be fascinating. So let's see. Okay. Any other questions? Recommend your favorite near accurate sci-fi movies. The last one I saw, which was good, was Interstellar. That was near accurate. The way the black hole, the supermassive black hole, was depicted made sense from a physics perspective. The time dilation that is experienced by the hero also made sense from a physics perspective. The last part of the movie, in which he goes into a black hole and encounters a tesseract or whatever, that was all hypothetical. But apart from it, overall, it was a very good movie. So that's one movie that I liked a lot. There's another movie called Arrival, which is nonsense. Some people say Arrival is so good. I found it ridiculous. Yeah, so favorite near accurate sci-fi movies. One is, like I said, Interstellar. There's another one called Solaris. There is one called, what is it called? It's based off a novel by Arthur C. Clarke, 2001: A Space Odyssey, which is about a sentient computer. HAL 2000, I believe it was called. There's lots. Maybe I'll make a video about movie recommendations. How about that? Okay, let's see something else. Maybe one or two more questions. Somebody is asking questions about history. Today is the day of science. Okay, I think how do scientists say that the universe is expanding? Because of observational evidence. You look at a galaxy, and so first of all, we have to decide how far a galaxy is from us. Let's say you discover a galaxy and you don't know how far it is. So you take advantage of certain things like standard candles, type 1a supernova, in which we can actually determine the distance from us, between us and them, between us and that place. So there are certain ways of discovering how far a galaxy is. So first we establish the distance. Secondly, we look at the spectra, the light spectra that come from the galaxy. And there are certain spectral lines that we know what are the wavelengths. We look for those spectral lines in a spectrograph, spectrometer, whatever. And then we will find, invariably, in all galaxies apart from the Andromeda galaxy, we will find that these spectral lines are shifted towards the red end of the spectrum. It's called redshift. Redshift happens when the light source is moving away from you. It's the relativistic Doppler effect. So you find that all galaxies are redshifted. And the further a galaxy is away from us, the more redshifted it is, which tells you that not only is the universe expanding, but the expansion is accelerating. So we have determined that the universe is expanding based on observational evidence. Hope that makes sense. Shall I take one more question? How to do independent research in mathematics or in theoretical physics? You have to become really proficient in the subject. If you can do that, then you can do actual research. The first thing in learning physics is to become really, really, really proficient in math. The mathematical methods that underlie physics, all your basic math, calculus, differential equations, integral calculus, differential calculus, linear algebra, matrices, blah, 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 all that stuff. Pick up any textbook of the mathematical methods of physics. Mary Bose is one, and so on. I may have a few here. And you need to get really proficient at that. You need to spend hundreds of hours solving math problems. There's no shortcut to it. Minimum time period 5 years. Dedicated hard work. You do that, you'll become really good at math. If you are really good at math, physics is the easiest thing in the world. Physics is all math. Physics makes a lot of sense, or entire sense, once you get the math down. You do that, you can do research. Of course, you will have to study the various theories. Quantum mechanics, even though you may know the maths, is a big shock to you. The first time you encounter it, and especially when you start going deeper into it. So you need to get into quantum physics, quantum mechanics, quantum field theory, quantum electrodynamics, chromodynamics. You need to also study relativity if that's what you're into. So it takes a lot of time to get there. But once you are proficient enough, you can do your own research. You don't need to be part of any university or whatever else. So that is the brief guide or roadmap, which is not brief, and it certainly is not easy. That's how we do it. All right, gentlemen, all right, ladies, all right, friends, all right, my dear earthlings, I am done for today. Thank you very much for all the wonderful questions. I'm getting lots more, but I'm going to have to stop it here for today. We'll do it again next week. We will continue these science episodes as well. This is what interests me the most. This is my core competence, and I really enjoy talking about science. So we will do this next week again, and we'll keep on doing it. Thank you very much, and I will see you in the next episode.